Hello. With 5.2, we are talking about systems of equations and graphical solutions. So what a system of equations is it's going to be two or more equations. Let's say two or more equations with, now we're going to say two or more unknowns. And just to show you an example of that, just looking down here in example 2, this would be an example of a system of equations. Here we have two equations with two unknowns in x and y. You can see a system that has three equations with three unknowns, but we're not going to do anything with that. We're just going to stick to two. What a solution is just like we've talked about in the previous sections. It's going to be a point x comma y. But typically it just has to make one equation true. But now our solution, it has to make both of our equations true. A point x comma y that makes both equations true. So it has to be true for the whole system, not just one or the other. So the first example we have is 2a, a solution of the following system. So what we have to do is substitute in our 2 in for our x, our 8 in for our y. So I'm going to start by rewriting the first one, x plus 2y equals 18, and then I'm going to set up a t-chart and then substitute my values of x and y in. So instead of x, I'm going to use 2 plus 2 times my y, which is 8, and then I have my 18 on the right. And then I simply evaluate this. 2 plus 16 is 18. Well, 18 and 18, we get the same thing. So we know that solution is true for that equation. However, in order to be a solution of the whole system, it needs to make both true. So now we take the second equation, and again, we set up our t-chart, and then substitute our 2 and 8 in for our x and y respectively. And we know they have to evaluate to be 6. We have negative 10 plus 16, which would give us 6 and 6. So it does make this one true as well. So we say yes, 2, 8 is a solution. So now let's talk about what it means for a point to be a solution of a system. If we were to envision a graph, so let's draw or sketch a graph here. So here's our x and our y axes. Now, if we have a graph of a linear equation, which would be a straight line. Oop, that wasn't very good. Let's try that again. Let's try it this way. There we go. I could draw that a little bit better. We know that every point on this line would be a solution. That would be the x-intercept, which is a solution. All these points in here would be a solution. The y-intercept, we know all those points are solutions. But as soon as we add a second line in here, let's draw this line like this. We know all the points on this red line are solutions of that equation. However, there's only one point, and that's going to be right here, that is a solution of both of those equations. And that's what we're determining. So by finding that 2, 8 is a solution of this previous one, that tells us that if we were to graph these lines, they would cross at the point of 2, 8. So that's what it means graphically if something is a solution. And that's kind of what we're going to write here next. So solution by graphing is we want to find that point of intersection. So we want to find the point of intersection. Sometimes we call this the POI. This is where those lines are crossing. And that point where those lines cross, that is going to be the solution of the system. So now example 2, we want to solve the system to the nearest thousandths. So first thing we have to do is graph both of these lines. Well, looking at the first one, in order to graph this easily, we could solve it for y. So we could rewrite this as y equals, and then add an x to both sides, so x minus 3. So to graph that, we have to go down 3 places and plot a point, and then our slope is 1, so up 1 over 1, up 1 over 1, and so forth. So that would be our line there. So now let's draw a straight line to connect those points. That's relatively close. So now what we want to look at is we want to graph now this line. So we have negative 2x plus 1. So we start at 1, and then the slope is a negative 2 over 1. So we go down 2 over 1, down 2 over 1, and so forth. And then we have to sketch that line. And that's going to be fairly close there. Now, we know that the solution of this system is going to be that point where those two lines cross right there. But when we look at this, we can see that it's not easy to identify what that exact point is because it's not crossing on some nice integer grid marks here. So this is where we have to use our calculator. So what we're going to do is we need to graph both of these lines. So in our calculator under y1, we're going to type x minus 3, and then in the calculator under the y2, we are going to type negative 2x plus 1. So go ahead and type both of those into your calculator under y1 and y2. You can see that's what you should see on your calculator screen. The next thing we're going to do is we are going to use that calculate feature again like we used in the last unit. So we're going to press second trace. So we're going to press second trace, which is that calc menu. Now here we're going to use option 5, which is intersect. Once you press 5, the graph is going to ask you, or the calculator is going to ask you, which curve do you want to be your first curve? Because you could graph a whole bunch of lines at once, but you can only find the intersection of 2 lines at a time. So you have to tell the calculator which 2 lines. If you only put 2 lines in, you're just going to hit enter, then enter again, then enter one more time. So you're going to press 5, and then first curve, enter, second curve, enter, guess. You can move your cursor if you want, but then enter again. So in the end, you're pressing enter 3 times, and then it'll come up with the intersection point. And here's what you should see when you're all done with that. And then, so we need to write the solution. The solution is going to be an x comma y. And if I round here, we'll say to the nearest thousands place, our x value would be 1.333, comma, our y value of negative 1.66, and that would round to a 7. This would be our solution of the system. And we know that we can check this by following the same thing we did in example 1. You can substitute in your x and y here, and it should make both equations true. Since we rounded here, we know it might not be exact. Okay, let's move on to the next example. So here we have a couple application problems. The first one, are the forces in the following system given by F sub 1 equals 18 pounds and F sub 2 equals 41 pounds? Meaning, do those two values here, do these values make this system true? So what you need to do, this is very similar to example 1 on the first page. We want to see if they are true or not. So what you're going to do is substitute both of them in to see if it works. So I want you to pause the video and try that out. So we find here that the forces for F sub 1 and F sub 2 work in the first equation, however, they do not make the second equation true. So we say, therefore, the forces are not 18 and 41 pounds. Okay, example 4. Now we're going to graphically solve the given problem. Chains support a crate as shown in the figure. The equations relating the tensions T1 and T2 are given below. Determine the tensions to the nearest 1 Newton from the graph. So what we need to do here is we need to graph these equations. Now we're used to seeing x's and y's, but we don't see those here. So what we can do is rewrite these equations with x's and y's. So we can let t sub 1 be equal to x, and then also let t sub 2 be equal to our y. So therefore, we can rewrite it as 0.8x minus 0.6y equals 12. And then our second equation, I'm going to write it in red, 0.6x plus 0.8y equals 68. So now in order to graph these easily using our calculator, we need to solve them both for y. So I want you to pause the video and solve for y on both of them. Okay, now what we have to do is graph these. Before we do that, you will notice that I left the slopes in fractional form. The reason being is if we divide 4/3, we'll get a repeating decimal. And if we use that repeating decimal, our answer would be tweaked just a little bit incorrectly. So we want to be careful to not do that. Okay, so now when we graph these, you'll notice that they're not in your window. So you have to adjust your window. Keep in mind, this is a y-intercept and this is a y-intercept. So your graph is way down at -20 and way up at 85. So you need to find where they are crossing. So go ahead and pause the video and adjust your window so you can see the intersection point on your screen. Okay, once you can see where those lines are crossing, now you can press second, trace, option 5, and then you're going to press enter 3 times. And you'll find the intersection point to be 50.4, 47.2. However, the problem tells us to determine them to the nearest Newton from the graph. So now we want to round them. So the first one would be closest to 50. The second one would be closest to 47. So this would be our solution. Okay, in the last one, we have two children set up a lemonade stand and sold lemonade for $1. We can get rid of this other sold here, and brownies for $2. One summer day, the children had 20 sales and made a total of $28. How many lemonades and how many brownies were sold? Well, the first thing we always want to do is define variables here. So we're going to let x be equal to something and y be equal to something. Since we're trying to find how many lemonades and how many brownies were sold, that tells us what we need to use. So we're going to let x be lemonades and y be brownies. Now, in order to solve for two variables, we know we have to have two equations. So we need to set up two equations. So it tells us that there were 20 sales total, which means if we take all the lemonades and add it to all the sale of the brownies, we get 20 sales total. We also know that they made a total of $28. So I'm going to go ahead and write that. So now we need to write an expression that represents the cost of something. Well, we know that a lemonade was $1. So that would be $1 times each lemonade plus $2 for a brownie, so $2 for each brownie. Now, as you know, we don't have to write that 1 in front of there, but sometimes it does make it a little bit easier just so we can see what we're doing. Now we have our two equations. So what we have to do now is graph them. This is where your calculator is going to come in handy for you. So in order to graph them, we have to solve them both for y first. So this first one, we want to subtract an x from both sides, so we get y equals, and this would be -x plus 20. And then in the second one, first thing we'd have to do is subtract the x and then divide both of them by 2. So we get y equals -x divided by 2 plus 28 divided by 2, which would give us a 14. Now we can use our calculator to graph both of those. So I want you to pause the video, graph these lines, adjust the windows if you need to, and then see how you did. So there I graphed y equals -x plus 20, and then y equals -x over 2 plus 14. We know that the solution to this system is going to be this point where those lines cross. So that's where we need to use our calculator to find out those exact values. So again, we press second, trace, and then option 5 for intersect, and then you're going to press enter 3 times. You can find the intersection point to be 12, 8. So either here, if you answer it as an ordered pair, that works out, but you want to make sure that you at least define your variables correctly because x represents the lemonade. So you want to make sure they are in the correct order here. Or you could say they sold 12 lemonades and 8 brownies. And then what you should also do is double check that. So if they sold 12 lemonades at $1 a piece and 8 brownies at $2 a piece, do you get $28? Yes. And you should also double check that if you add 8 and 12, do you find 20 sales? Yes, you do. Okay, that's all we have for the video. Please reach out with any questions.